Welcome to the lecture on the topic delay spread and coherence bandwidth. We have discussed that the wireless communication channel, the signals that reach to the receiver is generally using the multipath propagation. In the multipath propagation, the transmission is generally NOS, which means non-line of sight, and the signals reach using the phenomena of reflection, diffraction, and scattering. So suppose there is a mobile receiver, and the mobile receiver will receive the signal when it is traveling. It can be a line of sight component, and it can come through reflection, diffraction, and scattering. But you can understand that all will have their different amplitudes, and all will have their different delays. So in this lecture, what we are trying to establish is how this delay can be quantified. So to model this, we use channel impulse response h of t as a summation of n components, and starting from 0 to n minus 1 n components, and these n components are of the ith channel impulse response hi of t, and hi of t is nothing else but an amplitude of ai and with a delay of tau I for the ith component. So when we add all of them, then from 0 to n minus 1 we get the complete channel impulse response of the wireless communication system. So in a multipath propagation, if we want to establish the delay that is there in the various components, first we define what is called as the power delay profile. So we take the ith component that reaches, and we define the power of the ith component as mod ai square, where ai is the amplitude. So basically voltage square becomes the power. So here suppose at tau is equal to tau naught, the first component with power p naught reaches, which has a magnitude of a naught square mod. At t is equal to tau 1, we have p1 is equal to mod a1 square. At tau is equal to t2, we have p2 a2 square, so on and so forth to n minus 2th component, and finally the tau n minus 1 component having the power pn minus 1, which is an minus 1 mod square. So this thing here is said to be the power delay profile, where we plot the power versus the time. This is the power and this is the delay. And using this, we will now define performance metrics for the wireless communication system. The first one is called what is said to be the maximum delay spread. It is the difference between the first and the last part. So when in time, so when the first component arrived at tau naught, when the last component arrived at tau n minus 1, so sigma tau max is basically tau n minus 1 minus tau naught, which is basically the difference between the first and the last component arrival times. But here you can see there is no involvement of the amplitude of the received signal, or therefore the power of the received signal. So basically it does not account for the distance. Distance changes the delay at which the signal comes. Distance changes the amplitude and thus the power at which the signal comes, and therefore that is not involved in this profile. This is the basic limitation. So suppose there is only one component that is received. So suppose only one component, the first tau naught happens to be suppose at 5 microseconds. It is coming from a larger distance. So it comes at a time after a time of 5 microseconds. But in this case, this is the only component. Therefore, it also happens to be tau n minus 1. And in the formulation, you can see that if we take sigma tau, it will be tau n minus 1 minus tau naught. And in this case, the sigma max of tau will be therefore 0. So it does not account for the delay that has already happened, because there is only one component, and therefore it is not, even if there are multiple components and each are of varying strength, and it does not take the context of the amplitudes, therefore it is not that important. Therefore we define the most important thing, and that is said to be the RMS delay spread, where we include the power as a weighing factor. So basically, to define the RMS delay spread, you can now understand it's the statistics. RMS means root mean square, which is square root of the variance, and variance is always calculated as expected value of x square minus expected value of x, where expected value of x is nothing else but the mean. So we firstly define what is something called mean delay, which is just multiplication of the power multiplied by tau naught and its addition. So we take in mod a naught square into tau naught, mod a2 square into tau 2, so on and so forth to mod a n minus 1 square tau n minus 1. And in the denominator, since we are taking the mean, we'll take average of all the powers. So which means we'll take all the powers. A naught square is basically p naught and a n mod square is p n minus 1. So if we can write this in terms of a closed form expression as summation from I is equal to 0 to n minus 1 mod ai square tau I, the weighing factor of power with delay, divided by the summation of all the powers, that is I is equal to 0 to n minus 1 summation of mod ai square. Once we have defined tau I, the RMS delay spread is then defined for the given profile as mod a naught square tau naught minus tau bar square, which is tau naught is the time arrival of the first component, and suppose tau bar comes something here. So what is the difference between this component and this component? Similarly, mod a2 square tau 2 minus tau bar square, which will be the gap between these two components, and this will go like this. In the denominator we have still the summations, and since it is RMS value, it's basically the root mean square value, which means the square root of variance. So we'll take the variance, and therefore in closed form expression the sigma tau RMS is summation I is equal to 0 to n minus 1 mod ai square tau I minus tau bar square divided by summation of I is equal to 0 to n minus 1 mod ai square and the square root, where the mean we have already defined tau bar as summation mod ai square tau I square upon mod ai square. Now when we have defined the delay spread is the delay. Now delay is in time domain. We also want to understand about the frequency response of the system. So the delay spread therefore will be related to the frequency response through the LTI system model that we have followed for the multipath wireless communication system. So multipath wireless communication system will have the input of xt, the output of yt, and the impulse response, the ht, the wireless channel impulse response, is the through which we are acting it as an LTI system, and therefore the output will be simply the convolution of the impulse response and the input. So this is the impulse response, CIR, channel impulse response, and this is the input. So convolution of those two. What happens in frequency domain? In frequency domain, the output YF is simply the multiplication of HF and XF. Therefore, if we now want to check about the bandwidth of the system, or basically the frequency response of the multipath channel, then this will be modeled as this, that we have input in frequency domain XF, output as YF, and this as the frequency response. So frequency response is basically in terms of its flatness, in which range of frequency the channel operates. So from F1 say to F2, the bandwidths are generally defined as 3 dB bandwidth when it drops by an amount of 0.707 in linear range, and in decibels it becomes 3 dB less than 0. So this will be termed as the bandwidth of the channel. We generally assume it to be for understanding purposes a rectangular shape like this. When it starts from F1, ends at F2, nothing before F1, nothing after F2. So this is the frequency. Now this has to be related to the delay spread that we have calculated. Remember, this was the description in time domain and this is in frequency domain. So how can we go from time domain to frequency domain? We take the Fourier transform, and therefore we have the definition of the coherence bandwidth. So from the frequency response definition, what is frequency response? Frequency response is denoted by capital H of f, which will be the Fourier transform of the impulse response ht. So how do we take the Fourier response? Integration from minus infinity to plus infinity e raised to the power minus j 2 pi ft dt. So we integrate in terms of t, we'll get something in f, and that f will be the frequency response of the wireless multipath channel. But our frequency impulse response is basically summation of these n components, where I starts from 0 to n minus 1, ai delta t minus tau I. We can substitute this in this expression, and then we will have that hf is basically this impulse response and its Fourier transform. We can take the summation outside. ai also does not depend on the integration, so we can take this, and this will be our further evaluation. We take the summation outside, summation, and then integration ai delta t minus tau I e raised to the power minus j2 pi ft dt. The variable is t, and due to the involvement of the delta signal, it is only operative at tau is equal to tau I. So what happens is that we can substitute this by 1, and we can take t is equal to tau I in this integration to yield the integral value. And therefore the HF, the frequency response, is also summation I is equal to n minus 1 ai e raised to the power minus j2 pi f, and now you can see we are putting t is equal to tau I. So this is what is the frequency response of the multipath system, and it of course depends on the amplitude and the delays of each multipath components. Now assume that we have tau naught is equal to 0. There is only one component at I is equal to 0. This means that HF will be in this summation only I is equal to 0 is there, and we'll have HF is equal to a naught. What does this mean? This means that there is a time and frequency relationship that is yielding. Now we consider that there is only one component. What is the meaning of one component? One component means there is only delta of tau I. Remember, we are writing that tau naught is equal to 0. So tau naught is equal to 0, then this has only amplitude of a naught. And if the signal is a delta in time domain, its Fourier transform is basically a constant in frequency domain, which will have a value of 1 if it is 1, otherwise it will have a value of a naught. So what happens is that when we have only one component exactly existing at tau naught is equal to 0, we have a constant frequency response. This will change as long as we change this width of the delta signal. It will start becoming more narrower. So this thing is here the perfect straight line. So this is constant in frequency domain. Now this is not in constant. This is basically sinc function. So you can understand that this was rect, this will become sinc, and vice versa. So if you take a sinc in time, it will become a rect. So what we are trying to yield is that the basic thing that we know is that T and F are inversely proportional to each other. We reduce the width, we increase the bandwidth in the frequency domain, and vice versa. This is what is happening. So therefore, as I said, that when we took a naught is equal to 1, we had a straight line in frequency domain, and this yields the definition of what is called the coherence bandwidth. The coherence bandwidth is basically the range of the frequency over which the channel is perfectly constant. Coherence bandwidth in the context of wireless communication is the measure of the frequency over which the wireless channel frequency response is relatively constant, which is flat, and thus this yields to the most important concept of flat fading. The coherence bandwidth is inversely proportional to the delay spread of the channel. You can understand delay spread is the projection of time delays between multiple components, and its Fourier transform will yield what is the frequency response, and therefore it is inversely proportional to the delay spread. The delay spread refers to the range of arrival of times in the multipath components. The larger delay spread implies a narrower coherence bandwidth, and vice versa. So in a very rich environment, a scattering rich environment where there are multiple multipath components which are traveling, there will be delays of the first component tau naught, and the last tau n minus 1 will be very large. This will yield a very large RMS value and therefore a very small coherence bandwidth. What is the importance of coherence bandwidth? The coherence bandwidth yields the concept of flat fading. So when the bandwidth of the transmitted signal is much smaller than the coherence bandwidth, the channel is said to be exhibiting a flat fading. So flat fading is when the signal bandwidth is smaller than the channel bandwidth. We would like the channel to be constant as far as possible. For that, the signal bandwidth needs to be smaller than the channel bandwidth. Similarly, when this bandwidth, the signal's bandwidth exceeds, and very important, exceeds, it is larger than the coherence bandwidth, suppose it is denoted by B suffix C, then in that case the channel frequency response is not constant throughout the bandwidth of the information signal, and therefore the fading that will take place in this case is said to be frequency selective fading. We always want to convert our system to a flat fading thing where the channel at least behaves in a constant manner, not that it becomes frequency selective. So we can also mathematically and graphically represent this. When the signal bandwidth Bs is smaller than the coherence bandwidth, the phenomenon is said to be flat fading. The distortion will be less. There will be attenuation, but the distortion will be less. Distortion is changing of the state of the signal in frequency domain, but fading will be there. A0 will be there, but it will be less distorted. But when the signal bandwidth becomes more than the coherence bandwidth of the channel, then it becomes frequency selective bandwidth and distortion. To visualize this, understand this thing, that the output of the channel is multiplication of the frequency response and the spectrum of the signal. Spectrum of the signal will have a largest bandwidth of Bs, and frequency response will have a largest bandwidth cutoff frequency of Bc. So suppose the case when we have Bc is less than Bs is less than Bc. So in this case, the frequency response will have a highest frequency of Bc. The signal we are assuming has a Bs which is smaller than Bc, which means this thing is smaller than this distance. Bc is larger, and this is the case for flat fading. So in flat fading, when these two multiply, understand what is the phenomenon taking place? It is multiplication. So when frequency domain there is a multiplication of HF and XF, we have what is YF, the output of the signal, output of the channel. And since the coherence bandwidth is larger than the signal bandwidth, all of the signal non-distortively will be passed. And when you multiply 1 with 2, you will get 2, assuming that 1 has a magnitude of 1. So you will get 2 as it is, since the Bs is smaller than Bc. This is what is termed as the flat fading condition. While on the other hand, what happens? This flat fading, that we are saying that the signal bandwidth is larger than the coherence bandwidth. So this is my coherence bandwidth. The frequency response seems to be constant till Bc. Then the signal has a final value of in frequency domain of Bs which is larger than Bc. This is very important. So therefore the signal bandwidth is now more. What is happening again? From this relationship there is perfect multiplication. So when we multiply now 3 into 4, you can understand this signal does not exist beyond Bc. Therefore whatever part of the Bs is beyond Bc will not come at the output. This multiplication will only yield till Bc, B suffix c. This is because two things can only be multiplied if both of them are non-zero. If any of them becomes 0, the output becomes of 0. So when we multiply these two, we get YF, which will be till Bc only. So what happens to this portion? This portion. What happens to this portion? This portion is not coming at the output. There is distortion taking place, and this is because it is a frequency selective fading. And therefore in wireless communication system, the designers always will try to sustain to this characteristic, and we try to make the signal bandwidth smaller than the coherence bandwidth of the channel. The coherence bandwidth is related to the RMS delay spread. So delay spread is because of the multiple copies reaching at different time instances. So if we consider the frequency correlation to be 0.550%, it is denoted by 1 upon 5 sigma tau RMS. When we consider it to be 90% correlated, then it becomes 1 upon 50 sigma tau RMS. But the most important thing is that it is inversely proportional to the coherence bandwidth. So in this way we can calculate the coherence bandwidth given the correlation, frequency correlation, and the sigma tau RMS, which is the RMS delay spread. These estimates are called ballpark estimates. So thank you for watching this lecture. If there is anything that this lecture could help you, please like and subscribe the channel. And for any kind of research assistance or collaboration, you can comment on the videos. Thank you.